Once you've finished this nugget, you will understand which properties of the fuel are the ones that might be the main limiting factors for the use of this specific fuel in a specific process. You will also be able to estimate the combustion intensity for a suggested fuel, since that might be one of the crucial limiting factors. And finally, you will have an insight into how the end users values these things. When I have asked students what they want to use bioenergy for, I have usually got 1 out of 2 answers. Either they say that they want to produce electricity, or they say they want to produce a fuel for cars. But since humankind has used biofuel to produce ceramics, glass and metal for millennia, it is obvious that these things can be produced using biofuel also today. So the end user is not necessarily a car driver or a power station. The end user could just as well be a glass manufacturer producing glass jars for marmalade. But then the end user will have very strict demands on the fuel delivered, so that it does not inflict upon the reliability of the process, nor on the quality of the product. The rest training material is to provide a very short summary of some of the potential connections between energy sources and energy users. Do play around in this matrix a little bit and read the corresponding text to get some idea of the flexibility offered by the renewable energy sources and by the energy infrastructure. One of the most crucial parameters to judge the quality of a fuel and to see if it's suitable for a specific process is the attainable temperature. The adiabatic temperature is of course only a theoretical value, but it can be used for a first estimate. Another crucial parameter is the attainable combustion intensity, or the attainable temperature. This is usually quantified in watts per cubic meter and is a strong function of the firing technology. A third crucial parameter is the attainable heat transfer to the load. This can be limited by the properties of the heating goods itself, by the geometry of the firing chamber, and, at least to some extent, by fuel properties. A fourth important parameter is the flue gas composition. In such cases, when the combustion products are brought into direct contact with the product, may the flue gas composition have a significant impact on the final product quality, or indeed on the process lifetime. Last but not least, will the emissions and the environmental impact have an important role in the judgment. The emissions are partly determined by the fuel itself and its content of different elements. It is partly determined by the combustion technology used. It is partly determined by the available and installed flue gas cleaning equipment, and it is partly determined by the maintenance of the combustion and cleaning equipment. So if a specific fuel in a specific type of combustion equipment tends to produce excessive amounts of soot, then that combination is not suitable for a process located in or close upwind to a residential area. And that holds true whichever good properties the fuel may have. The same thing applies for the storage of the fuel. In case the fuel storage attracts rats or other harmful animals, or in case the material in store rots and causes bad smell, then no matter how good the fuel is from a technical point of view, it is still not a good choice. These and other social and economic aspects will have to be part of your final report, but let us now concentrate on the pure technical aspects of the fuel quality. We will do that by the use of an example. A project run by the Linnaeus University, well, then it was Växjö University, in 2003-2005 aimed to demonstrate how biofuel could easily be reinstalled in the high-temperature process industry. The aim of the project was only to demonstrate that all the technology needed to retrofit high-temperature processes was available off the shelf already at that time. An art glasswork was selected because glass is a very sensitive product and the quality demands at an internationally well-known art glasswork are extremely high. Since the whole installation was only aimed for a short time, no real effort was made to save the thermal energy of the gasifier gas. Thus, there was a significant thermal loss and temperature drop in the connection tubes from the gasifier to the furnace, and when the setup was dismantled, we saw that tar had condensed inside the tubes. But what we did put effort into was to include the gasifier and furnace combination into the process control system, so as to demonstrate again the versatility of the solution. The furnace was running for 2 weeks, producing high-quality glass. Due to the tax reduction on fossil fuel at the project time, the setup was again dismantled and the furnace restored again to LPG firing. But the aim of the project was reached. All the technology to reinstall biofuel into the high-temperature process industry was already available in 2005. According to the International Energy Agency, there is a shift in the industrial sector worldwide to replace the use of fuel with the use of electricity as the main energy carrier. This shift can be questioned from a strict thermodynamic point of view, but let's consider what it means from a fuel quality point of view. More than 80% of the world's electricity is produced using steam turbines and fuel firing, or nuclear energy, of course. The steam temperature in these applications is typically lower than 600 degrees Celsius. The steam quality is not affected by the combustion gas, since the steam raising occurs in closed tubes. However, too much corrosive gases in the combustion products may be a problem because of corrosion in the superheaters, as outlined in the Busy Plan Handbook, Chapter 4. Since coal-fired power stations may well have thermal powers of several thousand megawatt, it is not realistic to just switch to biomass, but co-firing is always one realistic way to go. Some people would argue that the biomass first must be torrefied. Others argue that pellets can be milled together with the coal. Torrefied material has advantages from a storage point of view, but non-torrefied pellets are cheaper. So, assume we have 3 major pathways to make use of the energy stored in biomass. First, it can be used more or less directly to provide process heat in industries producing everyday goods. Second, it could be used more or less directly to produce electricity, which is then used in factories to produce everyday goods. The third alternative is to convert the biomass into something completely new and to purify it so that it fulfills the demands put by cars or airplane engines. I will not offer you any definite answer to this problem. After all, you are taking a master program. But when you do the final essay for this part of the program, you will have to prove that you have understood the width of this nexus.